continuing our discussion on surface gravity waves. Today on the 9th lecture, we will talk about the pressure fluctuation in the surface gravity waves and show that the energy flux and propagation is related to the group velocity, and we will use the group velocity to characterize waves as either dispersive or non-dispersive waves. If the group velocity of all the constituents are same, we will notice that they are called non-dispersive system, and in contrast, if the group velocity keeps changing with wave number, we have a dispersive wave system. And this is a very interesting topic in various aspects of applied physics and mathematics. So, we will talk about in great detail about the dispersive waves. When it comes to surface gravity waves, if it is formed in a confined region, then we would also notice that we can obtain standing waves. This will discuss in detail and show how the dispersion relation becomes degenerate in this case. This will be followed by our study over dynamics of waves over water with varying depth, and we will notice that the waves those will be formed varies greatly in terms of wavelength and frequencies. We will be able to show that whatever may be the wavelength, we can write out a conservation equation for wavelength. And talking about ray optics that was developed for studying optics, we will talk about dispersion and ray paths for dispersive waves. One of you at the end of the class asked me a little more about deep water waves and shallow water waves. What are the particle paths? There were some questions regarding that. So, I thought I will just simply go through it once again. If we look at this surface gravity waves as a consequence of the linearized irrotational approximation, then the flow field is defined uniquely by only one unknown, that is the velocity potential phi, given like this. So, this is your a travelling wave solution. Having obtained phi, you can successively take derivative with respect to x and z to get the velocity components, and from the velocity components you can equate it to its Lagrangian description, which upon integration gives you the departure of the particle paths from its equilibrium condition given by x naught and z naught. So, take a look at this. This is the way it looks like, and then once you eliminate this x naught and z naught and t, you end up getting an equation of an ellipse here. And this is the general form of the semi major axis. And well, once again there is no square here, that is a mistake. So, I will correct it once again. So, basically then what happens is that is a generic expression for the semi major and semi minor axis. However, if you look at specifically for deep water waves, then h would approximately be tending to infinity or very large. Then if you write these in terms of the exponential form, then you can see that for h very large, this quantity sine hyperbolic k into z plus z naught plus h by sine k h, this part would go to this value, and so would be the other one, that cosine hyperbolic k into z naught plus h by sine k h. So, what happens as a consequence, A 1 is equal to B 1? Well, if you have forgotten, in case probably none of you have, if I plot let us say this hyperbolic functions, then what I find that cosine hyperbolic begins with 1 and then it goes to infinity, right. That is your cosine hyperbolic x. And if you look at the sine hyperbolic x, it goes like this. So, that is your sine hyperbolic x, that also asymptotes to infinite value and whereas the tan hyperbolic case, actually this goes like this. So, now you can very clearly see that when x goes to infinity, both of them asymptotes and becomes together, and you get this a 1 equal to b 1. So, what you get in a sense is circular particle trajectories, right. So, if I were to plot this particle trajectories, this is the bottom of the bed and then say this is the surface gravity wave, then what you are going to see is a clockwise trajectory, okay. And as you keep coming down, so this is your datum for the z axis. So, as you keep coming down, you are going to see circles of smaller and smaller radius. That is because of this factor coming down, right. E to the power k z naught will keep coming down, because z naught is negative there. As you go down, you will get these, and so this is how you get. And that is what we also wrote here, that all particles in the same vertical column will be in phase, and the trajectory defined by these particles will describe smaller and smaller circles for deep water wave. Same way you can look at the shallow water limit, for which the capital H itself will go to 0, then you can very clearly see that sine hyperbolic component will go to 0, while the cos hyperbolic component goes to 1. That is a consequence of that figure that we have drawn. Then what happens is, you can see this is your A 1 and this is your B 1. So, what you are seeing then, A 1, that cosine hyperbolic part would be much greater than B 1. So, what we are going to see in this case is, of course, we are going to see elliptic trajectories with the semi major axis elongated as compared to semi minor axis. You also note that the semi major axis, this part would not change very much with z naught, right, because they will be in the close vicinity of 1 itself. So, what happens is, as a consequence, here as you are seeing, the amplitude actually keeps coming down and it goes to 0 like this, and this is what you get. And in this case, if I similarly try to look at the envelope of the semi major and semi minor axis, I will find that A 1 would virtually remain same, right, and as I keep going down, this will become thinner and thinner, okay, and so on and so forth, right. So, this is what you are going to see in the shallow water wave. Now, what is a deep water wave? If that is what we need to find out, we can draw information from this trigonometric hyperbolic functions. Whenever actually you have k h greater than say 1.75, you will notice that tan hyperbolic will rapidly approach 1, okay. And you look at your dispersion relation, that is where you would see the tan hyperbolic part comes and it kind of saturates to that, and there you would see that this will be kind of valid. So, right. So, your k h greater than 1.75 is a kind of a threshold below which you can talk about intermediate range, and if it is far below, then you will say it is a shallow water, but anything above 1.75 you could classify it as a deep water wave. Okay. This is something that you know. Now, a bit of trivia or information. If you look at ocean waves, if you are very close to the continent, what is called as a continental shelf, there the depth of water is roughly around 100 meters or so. But you go to the open ocean, little farther inside the deep sea, there it would be something of the order of few kilometers, something like 4 kilometers or thereabout, right. And the surface gravity waves that we are talking about usually corresponds to roughly about lambda is of the order of 150 meter. Okay. And if you talk about h of the order of say 100 meters, even in the continental shelf, we are not talking about very close to the beach, but little farther, maybe few hundred meters away from the beach, then you would be seeing this kind of depth, and there if the wave is of this kind, that qualifies as a deep water wave. So, for all practical purposes, the waves that you would see in the sea, excluding the one very close to the vicinity of the beach front, they can be classified as a deep water wave. Okay. And this is what I told you, that you have probably your exposure in optics and acoustics, where you have talked about longitudinal wave, transverse wave, but this is a mechanical wave, and it has got this interesting property that the trajectories are not necessarily defining a vertical or a horizontal motion, but it is a combination of the two, and you get either circles or ellipses, right. So, this is one thing. So, now what we could do is we could also work out how the pressure varies. So, the pressure variation you can use what we have already derived is the Bernoulli's equation. Okay. What was Bernoulli's equation? Of course, take a look at it. It is an unsteady flow. So, you will have this term, and then you will have P by rho plus this was a constant which we can conveniently set the datum to 0. Now, what you can do is you can define the pressure fluctuation. What do I mean by pressure fluctuation? It is the departure of the pressure from the undisturbed value of the surface. Okay. So, basically then we will be talking about P prime is the pressure fluctuation, that should be your actual pressures, or that we have written in the Bernoulli's equation, and then we will be doing this, because minus rho z z was the actual pressure, undisturbed case, right, from hydrostatics, that is what you get. So, this is your pressure fluctuation. So, it is easy for you to now see from here that these two together is going to give us P prime. So, that is what we are going to get, P prime by rho is equal to minus del phi del t. So, I will write this as this. Having obtained the expression of phi, you can calculate this as rho a omega square by k and cosine hyperbolic this into the phase part. Okay. This, if I use the expression that dispersion relation, which tells us omega square equal to g k tan hyperbolic k h. So, I could simplify, and then I could write this as rho g a and cosine hyperbolic k z plus h divided by cosine hyperbolic k h, and of course, this remains the same. Okay. Having obtained the pressure fluctuation, we would like to talk about something which is of immediate interest to us, namely how actually the energy propagates. Why we are trying to talk about this? Simply for the reason that we have defined a new quantity, group velocity, right. I do not know how many of you are very intimately aware of this quantity. I find that the mainstream literature and the books, they do talk about group velocity, but do not emphasize its physical importance, and that is where I would like to emphasize it a little more. Now, having obtained these expressions, what I could do is I could try to calculate what is the energy and what is the rate at which the energy flux is propagating in the fluid. That is a very important consideration. So, let us talk about little bit about energy consideration. If we try to talk about energy, now I think we have briefly touched upon it. We have gone through this expression for dispersion relation, calculated the group velocity, and we have obtained the limiting values for the deep water waves, shallow water waves, and what we notice that the deep water waves go at half the phase speed, while the shallow water waves go at the speed of the phase. Now, we did talk about this energy flux, and I did make this observation, and I now think that a deeper appreciation of that last bullet would be in order for us to appreciate what really is the true role of group velocity. And this is unfortunately has been lost in not only in the appreciation of the physics of the problem, and in computation this plays a major role, and that is what we are going to see as we go along. So, having obtained this solution given in terms of phi, the velocities, one thing of course we can talk about is the kinetic energy, which I will call, let us say, E of k. How will I define this kinetic energy? Well, at any location I will calculate the kinetic energy of, say, per unit volume, and then what I am going to do is I am going to average it over a wavelength and integrate it across the whole depth. So, basically we are talking about a surface gravity wave like this. So, I will look at it and integrate the energy from the top all the way to the bed. So, basically we will also be integrating it from minus h to 0, and this will be talking about this. So, you can very clearly see that this dx integral is actually taking the average over a one wavelength, right. So, this we can say that this is your kinetic energy, okay, integrated over the depth and averaged over a wavelength. Okay. So, there you have it. we have this expression for u and w, we can plug it in there, and I will take the liberty of omitting the steps and tell you that you would get the x and z integrals, they are decoupled, and one of which the x integral will give in terms of a times cosine cos k x minus omega t or sine, and that has been squared. So, that would give you a kind of a expression rho g into eta square bar. So, this is like mean square wave elevation, that is your eta square bar is. So, I have eta as the wave elevation, I square it and I average it over the one wavelength, that is what we are writing. So, since eta is a cos k x minus omega t, so you can work it out, it is rather easy, right. What is this? This is going to be 1 over lambda eta square dx, right. That is the definition of eta bar square, eta square bar. So, if I do that, I plug it in here and then I work it out, I am going to get a square by 2, very straightforward. Now, that is your story for the kinetic energy, and we are looking at a very benign case of lossless wave propagation, and that would allow us to also calculate the potential energy. These are the major players in defining the energy of the system, because there are no losses, no heat addition, etc., etc. So, we can talk about the dynamics in terms of kinetic and potential energy. What will be it? Well, very simply stated, this will be actually the work done to deform a surface interface. From its undisturbed position. Okay. So, that is easily obtained, again I will call that as EP. What would that be? Well, once again I will write the pressure work done that I will find out for the deformed case going from the bottom minus h to eta, the deformed phase, and rho g z will be the pressure that will act over small element d z, and I am integrating over the whole thing. And as we have done it before, we will integrate over x and take an average. So, it is the same context, like kinetic energy was integrated across the depth, averaged over one wavelength. So, potential energy is also written in the same basis. So, it is the same thing, integrated over depth and averaged. Okay, so there you have it. Once again, these are simple algebra, you can do it yourself, and what you would find that it should be also equal to half rho g. You can anticipate that, right. If you are going to get a steady state where you are going to get a constant amplitude waves, what does it mean? Like we talked about earlier also, that would mean a perfect balance transfer of energy from the potential to kinetic, like your simple pendulum, right. It is a non-dissipative system. So, that is what you are seeing here also, and no prize for guessing that the kinetic energy and potential energy should look like the same. So, having obtained this, what we could do is we can talk about the total energy of the system. Well, that would be sum of this 2, and you find that should be equal to rho g square bar, that should be equal to half rho g square. Okay, that's that. Now, next what we are going to look at is, this is the total energy of the system. If I integrate it over the whole depth, that is what we are going to get. So, if that is the energy, we want to find out when the wave is propagating, traveling, what is the rate at which that corresponding energy is going as a flux, right. So, if I want to calculate the rate of transmission of energy across any vertical plane. So, rate of transmission of energy is basically the flux. This is then what we mean by energy flux, and this energy flux, which I will indicate by F tilde, that would be nothing but, what would it be? The pressure velocity work. Some of you would be familiar, some of you may find it little tricky, but that is essentially the thing. If I look at a dz element, P into dz is the force acting, and if I am looking at the rate at which it is going, the work done would be that force times displacement is dx. So, if I am trying to calculate its rate, that will be dx dt. So, that dx dt, that rate is given by this, and this is your force P times dz, right. So, that is your flux, that is the way the work is done per unit time for the displacement dx. So, okay, so work it out. Now, I have just erased, but you can look at your class note that P prime, this P is the pressure. So, I can write it in terms of the fluctuation. So, what I would get is F tilde would be equal to P prime minus rho g z times u dz, right. So, it has two component. One would of course be coming from the fluctuating pressure part, and the other part. So, this you understand. So, this is going from minus h to whatever eta or 0. I mean, it will probably take the corresponding linearized version and we will do that. So, you can set the limit here minus h to 0, and this is the other part would be minus h to 0. You have rho z u z dz. Okay. Now, as we have done before, we have reported quantities which are averaged over one wavelength. So, we retain that spirit and define f. So, that is basically flux averaged over one wavelength, and if I look at that expression, that would be nothing but f would be nothing but, I will integrate f tilde x, and this is what we mean. So, that brings like quantities. What we had talked about the energy, we are correspondingly finding out the flux which is averaged over one wavelength. And what do you find that when I am trying to average this quantity over one wavelength, what will happen? X dependence comes from here in E, u, and u expression that you saw was in terms of cosine k x minus omega t. If I take an average of a cosine function over one wavelength, that will give me 0, right. So, this part is not going to contribute, because the averaging process in x direction on u over one wavelength will yield the null value. So, what you are getting here, then you are getting this expression 0 to lambda and the z integral minus h to 0, and you are going to get p prime u dz to dx, right. So, you have the expression in front of you, and we can plug those values of the quantities we already have. We have the expression for p prime. Look at your notes today. You would note that f that we have written, that flux, the flux would then have the x dependent part that would have cosine square k x minus omega t. This is your x integral. So, this is that part multiplied by all those associated quantities rho a square omega cube k sine hyperbolic square k h, and we will be performing the integral from minus h to 0, and we will have cosine hyperbolic square k times z plus h. Well, we do not need this anymore. So, this times dz. So, there are these two quantities. I have decoupled the x and z integral, and once again you can figure it out that this will be half, right. This will be half. Well, of course, this a square, bring it here, that will give you a square by 2, and you have rho, and in place of omega cube I can use the dispersion relation. I can take omega square and put g k. So, if I do that, I am omitting steps. You can do it yourself, or if you are lazy, you can look at the book. There you will find that this expression is given by so essentially after all that what you are seeing that F is equal to, this is your E, we have just now derived the energy, total energy, and this expression is Vg. So, what you are seeing, what we expected to see was that the energy is being transported across any vertical plane is given by the energy that is being transported times the velocity, and that typical velocity happens to be the group velocity, not c, right. So, this is the physical implication of group velocity. It basically tells you the speed at which the energy propagates. This we have shown it for a specific example, surface gravity waves. But if you also recall, when we looked at the superposition of two neighbors, there also we seen that the amplitude propagates at Vg, and we related that amplitude to amplitude squared to energy. So, you are seeing the same thing. So, this is rather very important that given a physical system and we are asked to compute how the energy is propagated by that system, then we need to know the correct velocity scale. See, what happens is many a times we are so much preoccupied with our knowledge of simple linearized waves, where Vg happens to be equal to c, and then you do not have to distinguish between Vg and c, and you always draw a general conclusion out of a mistaken notion that Vg is always going to be c, and that is not the case. So, what happens is many of the physical systems that we will be looking at, we would be wary of finding out the speed at which the energy propagates, and if we are able to calculate that carefully, I mean that is a very important concept. And tell you what, this was there in original paper by Hamilton. You have heard of Hamiltonian mechanics, that same Irish mathematician Hamilton actually had in one of his paper talked about energy propagation speed, but it is probably Rayleigh who did a very good job and laid the foundation of group velocity, and he was the first to tell that group velocity is different from phase speed. Now, this is as I was telling you, if you are looking at 1D convection equation with C positive, you substitute a trial solution. A trial solution would have an amplitude and a phase part, and then plug that in over there, and you get this dispersion relation, and you take the derivative of omega with respect to k, that gives you the Vg, and in this case the phase and the group velocities are the same, and this is one of the property of non-dispersive system, whereas a large number of situations where you come across, including that surface gravity wave, what we see that Vg is not equal to c, because the phase speed itself is a function of k, and this part is non-zero, that makes Vg different for different k, and what happens in consequence that an initial impulse given to the system fragments itself into various components which will be traveling at their own group velocity, and you are going to see the different k component going at a different speed. Now, what you notice that the phase is defined by phase speed c, but if the energy is propagating at a speed which is greater than the phase speed, then what will happen? You would see that small wavelets riding on the overall wave packet, they will actually build up in the front, because they are going at a faster speed compared to the phase. So, you will see them building up in the front of the group, and because the energy is not there, so what happens? They will disappear from the back. Okay? So, this is something we will have to realize, that if the group velocity is more than c, then you will see the wavelet building up in the front, disappearing in the back, and vice versa. When the group velocity is less than phase speed, then you will see that the energy is lagging behind, while the system has the propensity to show that the phase can go ahead, and that is what will happen, that you would see that the wavelets will fall back, and because there is not any energy to support them, so they will keep disappearing in the front. So, next time when you are near a pool of water, you decide to drop a stone, you can see which case depends on the depth of the pool that you are looking at and the type of wave that you can create. So, that is what we raise this question, take a look at it. Now, one thing I wanted to tell you that so far we have been talking about waves which were going in the positive x direction. So, that is why the phase was defined as k x minus omega t. Now, suppose we try to discern what is happening with gravity waves which are propagating in the upstream direction, then its general description would be given by a similar expression, but you see the x t dependence on the phase is spaced by a plus sign. So, this will indicate that the wave is propagating upstream. And what happens? You go through that same analysis that you had done, you would find the dispersion relation appears with a negative sign. It is just that difference. Okay. Now, what you find, calculate the group velocity by taking its derivative with respect to k, and you would find the magnitude remains the same, but it appears with the opposite sign, and there is nothing wrong in that simple observation. However, that is where something happens interesting, that if we have two waves, one going in the positive direction, the other one is going in the negative direction, and if they decide to superpose, then what happens? Well, once again simple trigonometry will tell you this. Here is an interesting scenario. The system depends on x and t, right? However, they are disjoint, they appear differently, and we also notice some very interesting property that around k x equal to plus minus this odd multiplier of pi by 2, you will have eta equal to 0, right. If that is the case, then these locations are the nodes, right, with 0 displacement. And what happens here? I would get a kind of a space dependence that is given by cos k x, right. I have that, but the time dependence is a simple harmonic, right. So, what happens? All the points would go up and down in the same phase. That is what we meant here by the surface particles will oscillate in unison and the wave will not propagate. I am particularly bringing it to your attention, because if you look at that book by Kundu and Cohen, I think that is where they have made a mistake by claiming that there is a group velocity that is given by either the upstream propagating or the downstream propagating path, but that is not true. The energy does not propagate, because you do not have a space time dependence appearing together, right. You need to have them in a composite function which will be appearing together like what we have seen, k x plus minus omega t. So, if I have a limited body of water like lakes or ponds, then the standing waves get created. Why? Because if you recall the D'Alembert solution, we talked about the Cauchy problem. We took the interval going from minus infinity to plus infinity, and if I created a disturbance somewhere, then it can go in both the directions. Now, if I intervene by putting in some kind of a boundary, what will happen? Those waves will go there and reflect back, and then the incident and the reflected wave can create standing waves. And what happens? The dynamics would be given by this, because the nodes will be fixed at the source, and that will determine the fundamental wavelength, right. That is the longest lambda by 2 that you can get between the two shores, right. You will get half the wave, right. That is what you can get. Now, from this we also surmise that k and omega are not related. So, we do not have a dispersion relation, right. They are independently appearing there, and as I say that books tell you that dispersion relation remains the same, but it is not true. Here no energy is transported by the wave using the intervening media. Standing waves have this property. Now, there are some other interesting properties of surface gravity waves. If I create an impulse on the surface of the liquid, then what will happen? That simultaneously many harmonics will be created, and this is a case of a dispersive system. So, what will happen is that different k component will travel at different speed. What would you see as a consequence? If I give you a compact disturbance source, with time it will enlarge the region over which the disturbance is felt. Now, you have the expression for V g, and you would take a look and you would notice that depending on the value of k, you are going to see different parts going at different rate. What would you see at the leading edge? If you look at the expression for V g, you would notice that the smallest k travels at a higher speed. So, near the leading edge of the disturbance packet, you would see the longer wavelength disturbances. So, initially I may create disturbance which have let us say a compact basis, but then with time it will not only stretch, you will also see the longer wavelength to the right of the system, right. Now, that is a generic statement, but further refinement occurs when we start looking at the dynamics of the disturbances as seen if we are looking at those disturbances forming over let us say constant depth or a varying depth. In fact, this kind of variation of depth can add to very interesting situation. I think I can show you this picture, and this is what I was telling you. Probably this is not drawn very carefully, and that shows up what should have actually happened in this figure. The longer wavelength part should be on this side. See, this is a disturbance, this is the x axis, and the time is increasing like this. So, with passage of time, the disturbance is stretched over larger and larger x, and this part would be dominated by longer wavelength smaller k. So, this is not drawn very carefully as I should have done it. Okay. And now, what happens is, as we have seen, that it is no more a monochromatic wave. So, what is happening is you are going to see some kind of a displacement, which you would like to say that is a slowly varying function of x and t. Slowly it is changing, and the same way the phase would be written in terms of theta, which is also a function of x and t. How different is this theta of x and t from its slowly varying function? This will still be written here like k x minus omega t, but the important point to recall here is that k and omega, they are changing with x. They are no more a fixed entity like what we have talked about when we looked at monochromatic wave. So, what happens is, if I have a theta which we wrote like k x minus omega t, then well, I could take a derivative of this partial with d theta dx, a slowly varying function. I would just see this, write it as k, right. That is what we have here, that k of x comma t would be obtained by looking at the variation of phase function with x, and the same way I could differentiate this with respect to time, and that will approximately give me minus omega. This is all happening because we are talking about slow variation, okay. And if that is the way you look at the displacement and find its variation with x and t and talk about a local k and local omega, then you can further differentiate this one by with respect to t and this one with respect to x, and you see the right hand side will add up to 0. So, you see a very interesting property that for such slowly varying waves, that del k del t plus del omega del x goes to 0, and since this del omega del x we could also write with the use of chain rule in terms of d omega d k into del k del x. So, this d omega d k is the group velocity, right. So, what we are noticing that for slowly varying waves, that k is governed by this equation. This is like your convection equation that we had obtained for displacement or other physical variable. So, similar such thing is being noticed here for the wave number k, provided we track it at the value of V g. So, if we are going at the speed V g, then we would be always looking at the same k, because this is nothing but the total derivative, right, d dt of k. So, this tells us that if we decide to track the same value of k, then we should be fixing our gauge, and the gauge should move at V g, right. This kind of confusion occurs if you have noticed some of these waves in pond or confined space, and then most of the time what we try to do, we try to follow a crest or a trough, something of that kind. Then what happens is you see the following things. One, we have already said that as it goes outwards, what will happen? You are going to go over to a longer and longer wavelength, and then all of a sudden when your energy cannot keep pace with the speed V g that it has, then it will disappear, right. That is what you see. However, if you want to follow the same wavelength component, then you really must move your gauge with this velocity V g. So, if I now go back to my x t plane, then I should be looking at two sets of lines. One is given by dx dt equal to c. Those lines will tell me, those rays will tell me along which c is constant, right. And there is the other ray path that will draw, that is given by dx dt given by V g, is the line along which k remains constant, right. So, what we find then that at time t equal to 0, I have created some band of disturbances in this range of x. With the passage of time, that band widens because of dispersion effect, and then what I can see is that the ray path given by dx dt equal to V g defines where I would see the actual disturbances, because that is the speed at which energy is going. So, the extreme of that V g range will determine how this envelope is going to enlarge. Okay. and this thin lines tells you along which your phase is constant. So, if I am now looking at surface gravity waves, what happens is along this line k and V g remains constant, right, and these are the ones, those are indicated by the thick straight lines. The thin lines are paths of wave crests, those appear from the back, because why? We are looking at, let us say, either of the case. Suppose we are looking at deep water wave, then C is of course greater than V g, and for deep shallow water this will be C will be equal to V g. So, if we are looking at deep water wave, C will be greater than V g, and then what will happen is you will see that crest will appear from the back, yeah, and then they will disappear in the front. That is determined by the range of V g, admissible V g's. Okay. So, this range of k is of course decided by the initial impulse. How I have distributed the initial energy across different k, that I can get it from the initial condition. What happens later is a story that is dictated upon by the dispersion. As we note here, the ray paths open up with time, and this is a very important observation. If I create a disturbance at one point, with time what happens? You are going to see concentric circle, although we are talking about 1D wave propagation, but here x is more like your r, right, in a cylindrical coordinate system. So, the same energy is going to be distributed over larger and larger area. So, what happens? The amplitude must come down. So, when you see such waves, amplitude is coming down, it is not a viscous effect, it is not due to loss that the amplitude is coming down. It is because of distributing energy over larger area. That is another nice property of dispersion. And what happens? Because of dispersion, amplitude keeps coming down. So, as time progresses, you will have a better and better support for your linear theory, because the amplitude comes down, and that was our starting assumption for linearization, right. So, I will stop here and we will continue maybe a couple of more lectures and talk about certain very interesting properties of these